And then the next thing I want to show is the reaction that we have at both ends here. These are the chemical reactions. In the case of lead, this is a lead battery, okay? So there are other types of reactions out there. And what you see here is, again, the negative pole is on the right-hand side of your screen. The positive pole is on the left-hand side. And the right-hand one, the negative side, is related to the lead, whereas the positive or left-hand side is related to the lead dioxide, okay, which is a different you oxidize lead essentially. Pb, by the way, is plumum. That's the Latin for lead. Okay, and that's where they got the plumb bob. By the way, they used to measure the walls that the Romans built. They used to measure it with a plumb bob, and they also used to call that the perpendiculare, which was perpendicular to the horizon. So the guy who was out there. Where's my little ball with the string? Oh, I lost it. Oh, here it is. Okay. So they had the plumb bob held from a string, and they measured to see if the wall was straight. And since they did it against the horizon, there was a perpendicular. Then they got it from the plumb bob, which was called the perpendiculare.
Plumbing also comes from
plumbing
lead,
also
it used to be done with lead.
Yeah, and again, plumum is the Latin word for lead. We don't have any problem in Spanish because we call it plomo. So we use almost the same Latin word. So we have no problem looking at a PB there. Americans might have a different version. They would rather see a different code. But yeah, PB is plumum, lead. And what you see here is the reaction. You have lead plus H2SO4, which is sulfuric acid, and you're going to have a dissociation in the water and also in the reaction with the plate, with the sulfuric plate, with the lead plate, and you're going to end up with a sulfate, lead sulfate, which is that bluish, light blue PbSO4, and you're going to release two hydrogen atoms, but they're not atoms. You see a little plus sign right after that, 2H plus. That means that these two hydrogen atoms are anions. They've lost their electron, and they remain as two positive charges. There's only a proton. In fact, that's what they're called really when they lose a hydrogen atom that has lost its electron is known as a proton. Period. And that's how it's used in chemistry. They like to talk about proton and not to say, a hydrogen atom that's lost an electron or an anion. No, it's simply called a proton. But what's important here is what I circled there at the end and made kind of big. Should have made the one on the bottom also big, but two electrons. And since we don't know what an electron looks like, I just put a little E. It doesn't really have a code other than the E, and followed by a negative sign. That's what everybody understands for an electron. So the important thing is that we release two electrons into the solution. And those are the two carriers. That's why that lead, remember, we're trying to analyze what's happening on the right-hand side here, right? We had lead, Pb. We have sulfuric acid in water that's coming against that plate. There's going to be a reaction. It's going to release two hydrogen atoms. I'm going to show that in a second a little more graphically so it's not so abstract. And it's going to release two electrons, and these two electrons are what's going to make that plate charged negatively. That's what's going to be fed into whatever cable you stick, on that terminal. Okay, so that's why that plate is negative, because there's two electrons being released. Now, the first question a rational individual asks is, why don't the two electrons that are negative join up with the two hydrogen atoms which are positive? Well, there is no answer. The way this is done is with a magic wand. They say, well, all this hydrogen disassociated itself, it's running around as ions, as anions. positive ions. And the electrons are also like these little beads are floating in the water, also like loose, just waiting for someone to put a cable there. And you say, well, why don't they recombine and form, normal hydrogen? I mean, isn't that what hydrogen wants? Hydrogen wants an electron. And here's an electron floating around, whoop, chops it and gets it in, sucks it in. We're back to normal. And that's not the way they do it. They say, look, there's this reaction and these things are floating around. They have to justify where we got the two electrons. And you're going to see the difference with a rope model of light, which is really rational compared to this. This is no explanation, just says two electrons are free. It just is. Because we need those two electrons to show that how we're going to feed, the cable, the copper cable that you're going to connect to that terminal. That's why they've got those two electrons there.
Can't it be said that this chemical reaction only happens when you put a cable there?
No. The reaction is already there. The reaction has already created a storage of electrical charge. And what do we mean by that? We mean that it stored two electrons. Somehow, they're in the water just trying to escape the hydrogen now, because these hydrogen sharks, they're trying to eat these little electron fish, and the little fish are getting away, trying to escape the big shark that's trying to eat them. And that's essentially the explanation. You have no explanation, because they should recombine, and we should not see that equation there, that chemical equation. 2H plus 2E minus. You shouldn't see that, because the 2E minus should combine with the 2H pluses. Period. We're done.
If there's nowhere to go.
Right.
So what's happening on the other side?
Okay, and now on the other side, the brown side there, and again, I try to color code this as much as possible. This is the positive side, and here you started out with lead dioxide. It's an oxidation of lead. And some of the water, you've got this you got sulfuric in water, and obviously all these things react together. But the main part is that the water combines with the lead dioxide. And what it does, it produces 4 hydroxide. Hydroxide, yeah, OH. It's called hydroxyls. That's what they're called. But, it's OH. And what is OH? Well, it's just, you heard of H2O, that's water. Well, remove one H from that, and you got OH, and, the oxygen is still wanting something there. So, it's kind of waiting for for a reaction to happen. So what does it do? It borrows electrons from the lead, and lead has 4 electrons in its outer shell. So you have 4 OH, each one pulls an electron, and now lead is starved of electrons. It's missing 4 electrons. So it's positively charged 4 times. Not once, not twice, not thrice, 4 times. Okay? You removed electrons from the lead simply through the reaction. And so now lead has stored capacity, potential, whatever you want to call it. It wants electrons. So we've got on this side one guy who wants to get rid of electrons, which is the lead side, the one on the right. And you got the one on the left, the positive side. It's positive. It wants to receive electrons. It's starved of electrons. And that's the status of the battery before you plug anything to it. Here we have these two plates storing potential.
Does the water not affect the lead on the right side, and does the sulfuric acid not affect the dioxide on the left?
Yes, of course. There are different reactions. I put the simplest of reactions just for the ease of explaining, because I think what I'm interested in showing is not all the chemistry. I don't think you're so interested in that. You may not be chemically inclined. I think you're interested in finding out, well, what's going on in that secret world that we can't see? Well, what reactions are going on? And the important thing is, how does the plate on the right and on the left get their charges? Yeah. This is it. There are other reactions, but you don't need them. You don't need them to understand what you just heard here. In the one on the right, the lead, you got 2 electrons free for reasons that only God knows. And they're floating around together with the positive hydrogens, and for some reason they don't recombine. But the answer is that the reason they need those 2 electrons is that's going to be the charge that they're going to feed through the wires that you connect to the terminal. And on the other side, you create 4 positive charges in the lead by creating when the water reacts with lead and creates 4 hydroxyls. Hydroxyls take away that electron. I don't know why they have more power than the lead also. I mean, there's a lot of questions here, but let's grant that. What it is now the lead is charged positively because it wants to have an electron. So the guy on the right wants to give them, and the one on the left wants to receive them. That's a battery, okay? Now, what happens? Well, we're going to do a little, I'm going to show the reaction in a little more graphical way so that you can see it here. And what's happening here, you get sulfuric acid. This is the first one. This is the one on the right again. And what you have is sulfuric acid. And it's going to lose the 2 hydrogen atoms that you see there on the top and on the bottom, the gray ones. And you're going to have a sulfate ion, and that's going to combine with a lead ion, and you're going to release 2 hydrogen atoms, pluses. They're not even atoms, they're ions, and 2 electrons. And the 2 electrons are the ones we're concerned about because those are going to provide the charges on the plate on the right. And then we have the other side, the reaction on the other side. And again, I try to illustrate these things. Let me put them one right underneath the other. I don't think you need to see my face, okay? And here you see, let's see if I can put that a little higher. And here what you see is the what's happening on the left-hand side of that battery. You have lead dioxide. It combines with water. That's essentially the one that's going to do the trick. There are other reactions. It also reacts with sulfuric and etc. But this is the important part. And you're going to end up with lead with 4 positive charges because the OH, the hydroxyl, removed 4 of its electrons, stole it from it. And again, the question is, why don't they recombine again? Because that liquid is in constant touch with the lead. You would think that whenever it touches the lead, again, it delivers the electron back to the lead, that it stole. Or it would at least give 1 back, or 2 maybe. There should be all kinds of things in there. And no, they keep them separate because they need to explain why lead is positively charged on the left-hand side.
What happens to the dioxide part? What happens to
the O2? Well, the O2, see, you have 2 O2s there. In other words, look at PB dioxide, right? Yeah. You have the PB is the lead, that's the big ball there, and the 2 red balls are the oxides, right? Well, those 2 red balls plus 2 H2Os, I only put 1 in there because I just wanted to show the reaction, but if you combine those 2 oxide, 2 red ones, plus 2 red ones in the H2O, right? Put a 2 in front of that, and you got 2 more there. That's going to be your 4 red ones on the other side of the green arrow. And in the same way, if you put a 2 in front of the H2O, you're going to have 4 hydrogen, and that's also going to show up as 4 on the other side. I didn't put the numbers because I didn't think it was important. I wanted people to concentrate on the fact of how the charges are being kept, and not on the specific chemical.
Where all the atoms are.
Yeah. This is not a perfect chemical reaction because I was interested more in the physics of it, of what's happening. Lead is going to, in the bottom one, in the left-hand side, it's going to retain 4 positive charges because the OH, the hydroxyl group, stole them all, okay, out of its valence shell, which is 4. Okay, so now, let me put myself back here so you can see me again, okay? Let me drink some mate to get my energy.
Winding your ropes.